Hello and welcome. In this lecture we're going to be solving KCL and KVL practice problems to be able to master the concepts that we discussed in the previous lectures. So the contents are Falstad circuit simulator and an overview of that, and what this is it is an applet online that we'll be using to get an intuition, develop an intuition on how the circuits that we're analyzing behave. And the purpose is not really to use it as a SPICE engine, for example. The purpose is to just get a feel for, okay, we talked about conventional current, but how does that look like in a circuit? What if I add an inductor and capacitor later on, which we're going to learn about that. What if I add an inductor and capacitor? How does that affect the circuit behavior? It's really just to develop an intuition for the circuit so that when we look at the paper and solve these problems, we have some sort of an idea of what the physics behind it is. Although it's very simplified and obviously it's conventional current flow, so it's not actual electrons. But it is, I think it will be worth it to go through it for a few minutes for each problem and look at what that shows us. Then I'm going to talk about some recommendations given the necessary content, which is just to learn, first of all, the KCL and KVL and how to apply them. That's the bare bone essentials, the meat and potatoes of this lecture series. But to enhance that experience, I'd like to add the LTSPICE simulations, look at Falstad circuit simulator and try to use that to develop that intuition as I discussed earlier. And also, once we get to more complicated circuits, I'll be building some of these circuits, op amps, and measuring them. I'm still working on facilitating the necessary equipment, so we'll be talking about that later on. But this is something that I plan on doing and sort of closing the loop on and a whole lecture series on circuits and how to get the most out of it. But anyways, the recommendations will be on how to navigate these tools that we have and what steps should we take. In my opinion, that will be good to maximize what we take out of this lecture series. Then we're going to be actually delving into the KCL and KVL problems and talk about some nuances, the situations that arise, and what to do in this situation, in that situation. And really, I recommend that not only should you solve the problems before I do them, just to see, just to be able to detect where the problem areas are for you. It's very important that you actually solve the problems and not just watch me do them, because it won't stick to your brain as well as it would have if you solved them. You have to learn them yourself. It's not the goal is not to be passive and watch somebody do it, right? And lastly, we're going to take a quiz as usual, and I highly recommend that you try it before I give you the solution. Now let's go on and talk about Falstad circuit simulator. So this is an online applet that the sub section of that talking about circuits is going to be falstad.com/circuit. And why are we using this? Well, we're using it for a qualitative understanding of the behavior of these circuits, to be able to encourage the idea of analysis by inspection later down the road when circuits become more complicated, and in future courses where we have these multiple stages of operational amplifiers. When we look into the op amp, we want to be able to do things quickly, do the analysis quickly, and not write KCL and KVL every time, which is not practical when you talk about real world complicated circuits. For the quantitative analysis, we're going to be using LTSPICE. So although the applet will show you the values of current and voltage, we won't be necessarily relying on those. The purpose is not to look at those values. We'll use the SPICE engine to be able to get exact values at nodes and through branches. So let's talk about my recommendations, and keep in mind this could be different. This could be different for other people, for you. But what I think is reasonable here is to first inspect the circuit and predict its behavior. So I see some circuit. I see what elements it has. I use the laws that I've learned, some of the experience that I've learned to predict what it's going to do. I'm not looking for a particular voltage or current value at this point, but I just want to be able to get a feel for or predict what the circuit is for, what it's going to do. Then I'm going to analyze the circuit numerically using KCL and KVL, and then I'm going to simulate the circuit for intuition. And in this case, with the tools that we have, it would be with the Falstad circuit simulator, just to get a feel for, was that correct about that prediction? What is it doing? What is the current doing? What are the switching behaviors if I have a switch in the circuit? Things of that nature. And finally, I'm going to simulate the circuit for validation of the analysis that I performed in step 2. And the last step is optional, but it's a very, very good step, and if you're in school, this would be almost required. In most cases, it would be required, which is to build a prototype and test it, because the real world is not the same as a simulation. The simulation does not take into account parasitics, temperature. It can, but it usually is not as complex as the real world, with its many variables, the noise, variation in the supply voltage and current, and so on and so forth. So really, to get the most out of this lecture series, or in my opinion, any lecture series or any book for circuits, I would say that if you follow these steps, you'll be experiencing this, and you'll have a very good intuition and or problem-solving ability. So before we dive into solving the problems, let's briefly look at what Falstad simulator is. Let me adjust the screen here. So here I have it opened, and as you can see, as I was explaining, you can see some circuit here, and we're not going to worry about what these are or what it's doing. There's a capacitor, and there's a voltage source here and an inductor, but let's not worry about that. You can see here that the current is moving in a certain fashion. It's an AC current that we'll discuss in later lectures. There's some waveform here. You can measure the waveform across that inductor, that element, across the capacitor, across the resistor. You can switch in a different circuit, an auxiliary circuit on the side, and see how the power is dissipated, and that's shown in red. And you can change the simulation speed. If you make it slower, you'll be able to see the waveforms move at a slower pace, where you can increase it and have the time go faster. You can change the current speed, so the current that's shown here, the conventional current, will go slower or faster. So basically, you can see that it's useful to develop an intuition, and there are, let me decrease the speeds, and there are other circuits that they've already built in for us. They have AC circuits, they have other passive circuits, many circuits that if they apply, we will explore them on an individual or a case-by-case basis. But I just wanted to give you a brief overview on what this is and how it could be useful for developing the intuition. Now let's move on and get to the meat and potatoes of this lecture series, which is to actually solve these problems and learn the math behind them, basically. So in this problem, it's asking us to find voltage 1 and voltage 2 here in the circuit. Before I give it a try, go ahead and try this and watch me solve it. Okay, so assuming that you've given it a go, first question to ask here is, okay, what is this plus and minus sign here, and who's determining this? So with these problems, the way I like to think about them is if the polarity is determined, it's written in this manner. For example, what this is saying is, here's the plus end of the probe, either oscilloscope or multimeter, which we'll be talking about once we get to measurement equipment, or if we build the circuits and we're going to measure it, then I'm going to show you how you actually do that. But the idea is, okay, if this were a device that measured the voltage across that resistor, this would be the polarity we're using. We would be using this end, the positive end of the scope, the positive end of the probe, and the negative end in this manner. And what that means is, if we're correct about this polarity, and this polarity matches the actual polarity of the voltage drop across the resistor, then we're going to see a positive value. For example, let's say that's 5 volts. It's just an example. That's 5 volts, so we're going to see a 5 here on the scope. But if we were to actually flip that, if we were to just say, you know what, I don't want to say plus and minus in this direction, I want to say plus and minus in the other direction. I'm going to say it like this. Let's see. I'm going to say plus and minus here. I'm going to put this probe here and the other probe there. It looks kind of messy, but what you would see there is that it's going to be the opposite of what it was going to be had you matched the polarity. So it would have been a -5. That's all that means there. So let's just talk about that nuance there, because we're going to see it over and over again, and I wouldn't want it to be a mystery for you guys or girls. So let's clear these out of the way and go ahead and get to the next steps. So to summarize that point, what it means is that don't worry too much about these polarities. If it's given in the problem, all it's saying is that you could imagine it as, okay, the probes are hooked up here in that manner. So the plus n is on this side and minus n on this side, and if you flip those, you're just going to get a negative of what you would have gotten otherwise. but the rules will still hold, KCL, KVL will hold, and your circuit still has to obey the laws of conservation of energy. Okay, so let's go ahead and find those voltages then. So if we go ahead and apply a KVL, Kirchhoff's voltage law, I'll start here below the supply. I'll just go in this direction, and that'll be my loop. Just call that I. So what did we learn? So if I start from this node and I go up, I encounter the 40 volts, but I'm going to see the negative side first. So I'm going to have a negative, so the first equation, the relationship that I have is a negative 40 volts. And initially I'm going to include the units, but eventually I'm going to stop putting the units in. Right now it's good to keep track, but later on it's going to be repetitive and tedious to keep writing the units for resistors and voltages and currents. So negative 40 volts I'm going to encounter there, then I'm going to go up and see the plus end of this polarity for this resistor, so I'm going to say plus V1. And here's another problem. As we go through this, I'm going to just point out the nuances and things to avoid headaches as you solve these problems. I think it's always best to label a voltage across a particular element in this manner, and then just use that label to come up with to manipulate that variable. So for example, what I'm saying is, if you know there's, for example, 5 volts across this resistor, don't use that 5 volts and write that into the equation. Use the variable so that if you're doing KVL, for example, when you hit the plus side, you're just going to say plus V1. If you see the minus side, you're going to see minus V1. And you would see this, if you were to do it differently, you would see it in a problem where it would give you trouble and you would get the wrong answer, which I've done before and I've learned it the hard way. So I'm trying to tell you right now that I think it's best if you just use that variable and just manipulate the variables until the very end, instead of just applying, placing the numbers into the equations. So we're going to see negative 40 plus V1. Then I'm going to see here a minus sign here, but then the voltage itself is negative 10. So let's just call this guy Vx. Let's just call it Vx. And then I'm going to say plus V1 minus Vx. As I just mentioned here, I'm going to manipulate that variable, not the value, initially at least. So I'm going to see the minus, so I'm going to write a minus. Then I'm going to write Vx, regardless of what that Vx is, and we're going to save that here. We're going to say Vx is equal to minus 10 volts, just to keep that there. Then we're going to go here and see a minus V2. So I'm going to write minus V2. That whole thing is equal to 0. So the sum of all the voltages and voltage rises and drops must equal 0 in a given loop, in a given circuit. Now, what do we see here? We know that Vx is the actual value, so that's not really an unknown, but V1 and V2 are unknowns. So let's see. What are some other relationships that we could have here? So what we can do is simplify this equation. We're going to get negative 40, let's see, plus V1 minus V2. How do I want to write this? I would say plus V1, and then there's a minus Vx, but Vx is negative 10. So if I were to write that, I would say negative, I would put the Vx in the parentheses and get minus times minus is a plus. So plus 10 volts. And there's going to be a minus V2 equals 0. So what this is doing is it is relating these voltages, but I still have an unknown. I have a V1 that is unknown and I have a V2 that is unknown. And then I'm going to simplify these guys. Minus 40 plus 10 is going to be negative 30. Then I'm going to say negative 30 volts plus V1 minus V2 equals 0. Now, what are V1 and V2? So V1 is a current flowing from plus to minus here. We define I to be flowing from plus to minus in this loop. And so the current is going to go from positive to negative, and that's going to follow passive sign convention, which means that it's going to be a positive value. So it's going to be I times the 5 ohms. So 5I is V1. But V2, we're going to look at it and we're going to see that the current is going to go against the potential drop here. So it's going to go from minus to plus. So therefore, it's going to, according to passive sign convention, it's going to have a negative value. So it's going to be a negative I times the 1 ohms. I'm just going to write it this time because it's early on in the lecture series. So it's going to be 1 ohm. So to keep the unit's voltage, that's what we want to do there. So we know the relationship between V1 to the current and the V2 to the current. Now we're going to substitute that here. And let me just go ahead and move 30 to the other side. So I'm going to have 30 volts is equal to V1 minus V2. I just moved the 30 to this side. V1 is equal to 5I. And V2 is, let's see, this would be a minus because I haven't moved it to the other side. But then there's also a minus here, which is going to cancel that minus. So it's going to be a plus. I'm going to just write 1I. But that's going to equal 6I. Then I have 30 volts equals 6I. And what that leads to is, if I divide the 6 out, I get that I is equal to 5 amps. So that's my current. Now that I found current through this whole circuit, I can just plug that into the voltages and get the voltages. So you can see here that 5 times I is V1, so that's 5 times 5, which is 25 volts. And V2 is going to be, let's see, minus I, which is minus 5 volts. Because the ohm and the amp give you a volt, so minus 5 volts. Let's go ahead and circle these. And let's go ahead and find the power dissipated or dissipated or sourced by each element. So how do we go about that? So we know that the current's going in this direction, and my answer was positive. What that means is that the current is actually flowing in the direction that I originally specified. Here, so again, here's another nuance that is important to follow. If I have the current indicated as going in this direction, and my answer comes out positive, it means that it agrees with reality. So my convention here agrees with the reality of the situation, and the current is indeed going in that direction. Now, if the current value were to be negative, all that means is that the actual conventional current is going to be flowing counterclockwise and not clockwise as I indicated. So that's just something important to keep in mind. So given that, let's go ahead and find the elements, find the power dissipated through each element and be able to tell if this was correctly done. This is one way to check if the laws of conservation of energy are satisfied. So we're going to have 40 volts times 5 amps. That's voltage times current for the source. But then we have to remember that current's going from minus to plus. So the passive sign convention will tell us that it has to be a minus. And which means that the power here is being sourced by that element, which makes sense. It's a voltage source, so it's going to source some power to the rest of the circuit. Then we're going to go here and see there's a plus minus. Current's going from plus to minus, so that's going to be a positive sign. And it's going to be, what I'm going to use here is the I squared R law. I'm going to say the current is 5 amps squared times the value there, 5 ohms. It gives us a positive value for power dissipation, which makes sense because if the power is positive, it's being dissipated, and that's true for a resistor. Then I'm going to go here and say negative 10. I'm going to call that Vx again, and then say, okay, current's going from minus to plus, so I'm going to have a negative sign due to passive sign convention. Then I'm going to have a Vx, and I'm just going to skip a step and write Vx, which is negative 10, and write the current, which is 5 amps. And finally, I'm going to say, okay, the current is going it's going clockwise, so it's going to go from negative to plus here, and that's going to be a minus sign again, and that's going to be V2 times 5 amps. So V2 is what? Negative 5 volts times 5 amps. All of that must equal 0. So now let's see, is that true? So negative 40 times 5, so that's going to be 200, negative 200 watts plus 5 squared times 5, so that's what? That's 25 plus 5, that's 125 watts. Then I'm going to have a minus and a minus, so that's going to be a plus. That's 50. There's going to be 50 watts dissipated there. 50 watts there. Then I'm going to have a minus times a minus, that's a plus. That's going to be another 25 watts dissipated there. And lo and behold, we have that 50 plus 25 is 75, plus 125 is 200. That's a plus 200, minus a 200, that's equal to 0. So the laws of conservation of energy is satisfied. And let's go on to the second problem. Now in these ones, I'm not going to keep finding the power because we already demonstrated that. I encourage you to actually go ahead and find the power again for each element and verify that the law of conservation of energy was satisfied. If you do it, it's already been a long video, and sometimes you have to make changes on the fly, and it looks like if I keep doing that, it's gonna, for the rest of the problem, it's gonna take way too long. So I encourage you to go ahead and solve those yourselves, that additional optional step. So find voltage V0 and I in the circuit below. Let's see here. We have another loop. So when we're seeing loops, we're thinking KVL, because if I were to write KCL, it's kind of a trivial equation that results from that, because you're saying whatever the current is going into that node, into any given node here, is going to go out of that node, and that's not really very helpful. So we're going to use KVL a lot in this first set of problems. So again, we're going to look at the current direction shown. We're going to see that it's a clockwise current. No worries if you get a negative sign, that just means that, no worries if the actual direction of the current was the opposite direction. We're just going to, a negative sign is going to pop out somewhere, and we're going to know that we've done it correctly in terms of direction. So really you're seeing here in these problems that the magnitude and the direction is what matters, and we're going to be worrying about those things. So let's go ahead and apply these rules again. So I'm going to just start from here. That's where I like to start. Personally, you could start anywhere you like. I'm going to start here and go up clockwise, and I'm going to see what I'm going to see for the first problem, that I have a negative, for the first equation I have a negative 10 volts. I'm going to start dropping out that voltage. So negative 10, the unit, I'm going to drop that out. Negative 10, I'm going to go up, and it looks like I haven't labeled this, but because I have said that the current is going in this direction clockwise, therefore the polarity must be in this direction. And I'm going to stick with that, and it looks like I missed out this guy on the bottom. This guy was given, the V0 was given. That's where the probe is located at, the way the orientation of the probe is, if you'd like to think about it like I do. But for this guy, I'm just indicating what it is, and we'll see if I'm right or not. These laws will take care of the reality of the situation, as you'll see. So negative 10 volts, I'm going to go up, and I indicated this, so I'm going to see a plus minus here. Current's going from plus to minus, that's a plus. So a plus, I'm not going to label that, I'm just going to say 2I. 2 ohms times I. Then I'm going to say a plus here, that's going to be a plus 3 V0. V0. Then I'm going to go and see a minus here, that's a minus 2 volts. Let me drop that out. Then I'm going to go down here and see a minus. That is a V0. All of that must equal 0. Here's another relationship to have, though. Relationship is that V0 is equal to the current flowing here times the resistance, which is Ohm's law. But the current's going, as has been indicated, it's going from minus to plus, and therefore we should have a minus sign, and we're going to have a 4 ohms times I, and it's going to give us the V0. So now let's see what we have and what we're looking for. So we don't know what I is, so that's a unknown in the equations. We don't know what V0 is. For both of these, I'll solve that in a second. And in the second equation, we have another relationship between V0 and I, which is perfect because we have 2 equations and 2 unknowns. And that's what I meant by the prerequisite of algebra, which is that you should know that if you have 2 equations and 2 unknowns, you'll be able to find those unknown quantities. So really, we're striving for all these problems to be able to derive enough relationships, enough valid and non-redundant relationships that will give us the unknown variables that we're looking for. That's kind of one of the corollaries of this, what we're trying to do here, an effect that shows up again and again. So let's go ahead and, since we know what V0 is, let me first simplify this equation. So that equation is going to be what, negative 10 minus 2 That's going to give us a negative 12. Let me just go ahead and quickly get to the bottom of that. Then there is a 3v0 minus v0. That's a 2v0. Now, apologies if this is taking too long. I'm just trying to make sure that everybody understands every single step here. Otherwise, this would have been solved way quicker. So minus 12 plus 2 v0 plus 2I is equal to 0. Plus 2I is equal to 0. Now we have this other relationship that relates that we can substitute this v0 with I. So I'm going to go ahead and do that. So I'm going to have a negative 12 plus 2 times v0, which is negative, oops, I missed a 2. 2 times negative 4I. Let me write the 2I here equals 0 and then put a plus there. Now let's just go ahead and quickly do that part. So let me move the minus to this other side and say 12 on this direction. Then I have a minus 4 times 2, that's minus 8. Plus 2, that's a minus 6. I have a minus 6I, no worries. I divide that out, the 6 out, and I get I is equal to minus 2 amps, it looks like. And we're seeing a minus current. Not to worry, all this is telling us is that the direction that we indicated here is not the true direction of the current flow, conventional current flow. That's important to keep in mind. The conventional current flow then is going opposite due to this negative sign. It's going opposite of what we indicated. So the real flow, current flow, is going in this direction. But we can keep the same sign, we can keep the same convention and just keep carrying the algebra out, keep carrying the math out. Or we could just flip it. We could flip the polarity or the direction of the current to the true direction and get this negative sign out of the way and call it plus 2A. But if we were to do that, we would have to change all of these equations and change the polarities for all these voltages. So it's up to you what you want to do. I think it's easier to keep the math as is and just note to myself that, okay, this is the convention that I chose initially. Let me not change things up and mess things up. Let me just keep in mind that I should keep this negative sign throughout the rest of my calculations. So we found the current, but that wasn't all we had to find. We had to find V0 also. V0 is going to be negative 4 times I, but I is minus 2, so minus 2 times minus 4 is going to give us 8 amps. Or sorry, 8 volts. So that's our final answer for these two quantities. And I encourage you to go ahead and find the power dissipated through each element given the previous example. And let me check my notes and make sure I did this problem correctly and that the answers are correct. Let's see here. So I have minus 2 amps and 8 volts, and that is correct. Let's see if there's any questions to consider. One point that I would make here is keep in mind, as I was going through this, I was trying to think of it as a beginner student and see what a beginner student would think about this. I would just say that make sure that for sources, let's see, P equals IV must indicate direction of current according to passive sign convention. So obviously, think of sign convention, but also use P times IV for sources, and use, let's see, use P is equal to I squared R for elements, and specifically resistive elements, resistors. Let's just say resistors. If you use these two, I think it will be easier, because if you're using P equals IV for the resistor, you'll need to know the voltage across it, but you may have not found that quantity yet at that point. So it might just be better to use I squared R for the elements and I times V for the sources. So that satisfies that there. Another important point is that since you're looking at I squared R here, what this is telling you is that it doesn't matter for the current, for the resistor, the power is always going to be dissipated. So don't worry about determining that minus sign or plus sign when you're writing the equations that we saw for the previous problem. If you recall, I was going through and thinking of what the sign should be. But if you were to use I squared R for the resistor, you would just get the positive value for resistance and for power to the resistor, and that will take care of that. So just use IV for sources and I squared R for resistors to simplify your life. Now let's go ahead and go to the other problem. Move to the next problem, which is I need to find a way to move this guy. And this is turning into a long video, so I need to keep going now. So in this other problem, then it's a sort of similar problem. So it's saying find Vx, V0, and power dissipated. But because I've done that in previous problems, I'm just going to go ahead and negate this statement, and I'll let you handle that. And if you have any questions, I'll be happy to answer those on the comments. It should be pretty straightforward. Just follow those rules that I gave you through. So find Vx and V0. So again, we're going to see that we have the current direction set. We have some voltages, some dependent voltage source, some variables here. So I'm going to go ahead and we're going to see that Vx here depends on this value, and it's already indicated that the polarity is in this direction. So let's go ahead and write our KVL now. I'm not going to repeat the same thing, so let's just go ahead and rapid fire go through them. So negative 60, oops, I don't want everything to be red. Let's see, negative 60. I'm starting here again, going up there with the current flow with that direction that I indicated, or the problem indicated, and I'm going to say plus Vx. Let's go ahead and write plus Vx. Again, let's keep it in the variable form so that we don't mess any directions or signs up. Then we're going to go ahead and see another Vx. That's going to be a plus Vx there. Then we're going to see a minus V0. So minus V0, that's all equal to 0. That's one relationship here. Then some other relationships would be, well, what is, let's see, Vx then is going to equal, I is going from plus to minus, so 5 times I is going to give us the Vx. Now let's see, do we need anything else here? Then there's another problem, there's another relationship, which is that V0 is equal to currents going from minus to plus here in this direction. So passive sign convention tells us that it should be a negative. We're going to see a current go from minus to plus, that's negative. Then there's a 10 ohm resistor there, so that's going to be 10I. Okay, so we found the relationships, and let's look at the equations. We have, in this first relationship, which is based on a physical law, KVL, we have 2 unknowns, so Vx and this guy, V0. So we need at least 2 equations. So because our second equation has another variable I, then we need 3 equations. So let's see, let's go ahead and solve this nicely. So for the first equation, I'm just going to simplify things and take 60 to the other side. It's going to be a plus 60. That is equal to, there's 2 Vx's, so that's a 2 Vx minus V0. And then that's that relationship. Then I have let me just separate these. Then I have the fact that V0 is this value and Vx is 5i, so I'm going to substitute both of those in there and get that 60 is equal to 2 Vx. Vx is 5i, so that's 2 times 5i, that's 10i. Then we're going to have minus, V0 though is a minus value, minus quantity, so there's a negative quantity there. So minus a negative value is going to be plus. We're just going to negate that, so that's going to be 20i. So what this tells us is that 60 equals 20i, and if you take a 20 on the bottom there, so let's see, 60 over 20 equals I, that's going to give us a 3. So I is equal to 3 amps. And we're getting a positive value, which means that the current is indeed flowing in the initial direction indicated. Now we're going to find Vx by simply plugging in I into this equation. So that's 5i, which is 15 volts. Then we're going to have a V0, which is equal to negative 10i. We put that 3 in there, we're going to get negative 30 volts. And again, I recommend that you go ahead and verify that each element, what the power dissipator or source by each element is, and make sure that it follows, it satisfies conservation of energy. Let's see, do I have any notes for this guy? It looks like things were solved correctly here, so that's good. Okay, let's move on to the next problem. Let me save my workbook here, just in case. Okay, so find V0 and I0, and let me take this guy out. Now in this problem, things are a little bit different because we don't have a loop, and we have multiple loops, and we're seeing that we could be using KCL here. So I have some dependent current source I0 over 5, and I have some current I0, which is indicated here, that's given by the problem itself. Then I have a V0, then I have 4 amps independent current source there. So let's go ahead and, because we're seeing that we have currents here, it's probably useful to use KCL, Kirchhoff's current law, to relate the currents together. So let's see, the current here is going in this direction. Let me just indicate that like that. 4 amps is going in this direction. I'll say that. I0 is already given to be going in that direction. So let's just say it's going in that direction. So I'm going to use the alternate form of KCL, which is I'm not going to write something plus something minus something equals 0. I'm just going to say whatever enters is going to be summed with everything else that enters, and then that's going to equal whatever leaves. So what I mean by that is, okay, this guy's entering, that guy's entering the node, this guy's leaving the node. So let's say let's just put names, or I'm trying to think, should I put names on this? Yeah, let's do a name on that to make sure we understand the concept first. I1 is there, I0 is already has a name there, and let's make a different color too, make it nice, yellow, go the whole 9 yards there. So let's say 2. Now this relationship KCL, the alternate form that we discussed in the previous lecture, would tell us that I1 plus I2 must equal I0. Okay, so that's the relationship there. Now let me just substitute the current values. I1 is going to be I0 over 5. So I1 is I0 over 5. And this is probably a good practice to have initially, at least. Start with the principle, start with the bare bone facts and the variables, and then just substitute through, just because you want to make sure on your exams, your homeworks, just in general, try to minimize mistakes, of course. But some mistakes are good to see and learn early on, but it's probably good practice to just do certain things from the get-go, stick with the right conventions. So I have I0 over 5 plus I2, and I2 is 4 amps, so that's going to be this guy, 4 amps, is equal to I0. And I0, we don't know the value explicitly, but we're seeing here that it's going through this resistor, and we can apply Ohm's law. And Ohm's law would say that, let me just write I0 for now, and then go and make another relationship, and call that, use the Ohm's law there, so that's V0 is equal to, polarity matches the passive sign convention, plus to minus. The current's going from plus to minus, so I have 2 times I0. So that's good. Now let's see what we have here. So we have one equation here with one unknown, and another equation here that relates another unknown. So let's see, does that satisfy what we need to do? Let's go ahead and substitute equation 2 into equation 1, and that's going to be by way of saying I0 is equal to V0 over 2. So then I'm going to have V0. Here you see I0 over 5, so I'm going to have put in V0 over 2 there. So I'm going to have a V0 over 10, because 2 times 5 is 10, plus 4 amps is equal to I0, which is V0 over 2. Then I'm going to solve this to get V0, and then plug that in to get I0. So let's see, so 4 is equal to, let's take V0 over 10 to the next, to the other side. Let me factor that out and get, let's see, 1 over 2 minus 1 over 10. Find a common denominator. We get, let's see, that's a 5 there. That's 5 minus 1. That's over 10. Does that make sense? Yes, I got a common denominator. I have a 4 here. Then all of that is equal to 4 amps. We're going to ignore units now, because we're making sure that it's set up correctly in the beginning, so we can ignore the units. So then we have V0, 4 tenths, then I have a 10 there, 4 there. It looks like the 4 is cancelled, 10 on the other side. So V0 is going to give me a 10 volts. That's what I have there across. That's the voltage drop across that resistor. And with it being a positive value, it means that it's matching the polarity indicated. So I'm not going to worry about anything there anymore. Then I'm going to look at I0. And I know the relationship between the two, so I'm going to say, okay, I0 is whatever V0 is divided by 2, so I0 is going to be 10 over 2, which is 5 amps. And again, it's positive, so the polarities were guessed correctly initially. Okay, so that takes care of that. Very simple there. Apply the KCL problem there. So let me go ahead and do another KCL problem, and we know that because we have multiple branches and common nodes between them, so that kind of shouts KCL to me. Okay, so let's take out this section of the problem again and go ahead and solve for V0 and I0. Now, in this problem, here's another interesting fact. In making these problems, because of the fact that the KCL and KVL hold and the physical relationships hold, because of that fact, I didn't have to worry too much about making sure that each value satisfies the rule, because the conservation of energy, because whatever, these rules are so robust and nice that whatever the values of these elements are, as long as you follow some basic rules, for example, make sure you don't have multiple current sources in one branch, you don't want to violate KCL, KVL, don't have multiple voltage sources in one, in parallel, basically. As long as you don't break these laws, then you'll see that when you're making these problems, which is good practice to do, when you make up these values in these architectures, it doesn't matter what value you choose, because at the end, the power of the conservation of energy will be upheld, and the voltages, and what's going to happen to maintain that rule is that you're going to have the currents and voltages across each element and through each element redistribute themselves in such a way that the conservation of energy is satisfied. So that's a very nice fact for the person making up these problems, is that you don't have to check every single time conservation of energy, what it indicates. And you can prove this to yourself by just changing some of these values and seeing what happens. It's a very nice exercise to do. So let's go ahead and find V0 and I0. Again, it's a KCL problem, because if you were to do KVL, it wouldn't be nice here, for example, because we don't know the voltage here. We know it would be V0 in this case, because these are all in parallel, but in general, it wouldn't be good if you have and we'll get to this later, but let's just go ahead and use KCL. When we do super meshes and super nodes, we'll talk about all these things. So here we have currents is indicated, and I'm just doing this because it makes sense in the alternate form to say, okay, I have 10 amps of an independent current source going in this direction, then I have some I0 going in that direction, and this guy, this matches nicely with the convention, and it's just nice to do. Don't worry if you pick the current to be the opposite of what I'm doing, or just different. The correct answer will manifest itself if you do the algebra correctly and consistently. Remember, it's very important to, no matter what sign you pick, you stick consistent with the relationship. What matters is that the relationship, the algebraic relationship between these quantities is what matters. And it has to be kept consistent with whatever sign you choose. So let's go ahead and say, okay, so 10 amps is going in that direction, so that's KCL, 10 amps going in that direction is equal to, the alternate form tells us whatever enters is equal to whatever leaves. So that's going to be I0 plus I0 over 3, very nicely matching my convention, what I've used here for the current. Then I have some current here going through this resistor, but that is V0 over 6, that's just Ohm's law. And it matches the conventions that I've written here, current going in this direction and plus and minus for the voltage there, so that's nice. Now, what do we have? We have one unknown, two unknowns. Now, let's see, what else can we do here to, and I'm not recalling what exactly I did here. I need another relationship. Let's see, this was problem 5. So what other relationship did I use? So then I just used the simple fact that, okay, V0 is, let's see, V0 is equal to 2I. Right, okay, that's what it was, right. So what this is telling me is that since these are in parallel, V0 is applied to every single element. So every single element has a plus here, minus here. Every single element has a V0 applied across it, because a V0 is given here and these guys are all in parallel, so therefore every single one has a V0 across it. So we can relate I0 and V0 in that manner. We're going to say V0 is equal to 2 ohms times I0. So 2I0. I want to make sure you understand this, because since these guys, we developed this theory earlier in earlier lectures, and since these guys are all in parallel and they're sharing the same node, then they must have the same voltage across them. So plus V0 is going to be the voltage. We have two relationships. I'm going to substitute this equation into that equation, 2 into 1. So let me indicate that 2 into 1, and I'm going to get 10 is equal to I0. Let me factor I0 out and say 1 plus 1/3 plus, let's see, V0 was what, 2I. So I'm going to have a 2/6, which is 1/3. Let's see, is that correct? Because I put a V0 with 2I, so that's 2 over 6, which is 1/3 I, right. So you factor that out, then you get 10 is equal to I0, common denominator would be 3, then I have a 3 there, that's a 3 plus 2, that's a 5. So let's see, I want to make sure I'm doing this correctly, because I'm not going to check the powers. So and in this problem, let's actually go ahead and check the powers. It's actually a good exercise because it's a different situation. So I'm going to have that 5 cancels with this 10 and leaves me a 2 here. 3 goes to the other side and gives me a 6. So I0 is going to be a 6 amp current, and let's circle that guy. That gives us that, and we have V0, which is let's see, I0 times 2, which is 12 volts. Now, since we've already come this way, let's just go ahead and find the power dissipated or absorbed by or sourced by each element. So V0 is a positive quantity, which matches with this convention. So the voltage applied across this guy, this circuit, is going to be a whole 12 volts. How do I indicate this? Let me just write it. It's going to look bad, but 12 volts here is applied, and the current is also positive, so I0 is going in this direction, indeed. And so with this guy, because there's no negative here, so this guy's going to also go in this direction. And since the convention for the voltage was correct and we guessed it correctly, it's going to also go in this direction, the current. So therefore the 10 amps must be flowing in this direction. So everything is verified and nice and matches with what we talked about. So it was a good guess to set those conventions up. Now let's do the calculation. So we have 10 amps going in this direction and in a clockwise direction, and we have a plus and minus here. It's going against the convention there, against from minus to plus, so that's a minus sign. Remember, for sources we're going to say I times V, that's the power, so 10 amps times the voltage, which is 12 volts. For resistors we're going to say I squared R. That's our that is our convention. Let me just use a plus here. Let's see, that's a plus, that's a plus, that's going to be, so I'm going to have I squared R, so that's 6 squared times 2. I'm going to have a, let's see, what's the current here? That's a V0 over 6, which is 2 amps. I'm going to say 2 amps squared. There, so V0 over 6, yeah, that's 2 amps squared over or times 6. Then I'm going to say this guy is current is going from plus to minus, so this guy is a dependent source, but it's also consuming the power generated by this current source, the independent current source. So that's going to be a minus, or sorry, let's see, plus, yeah, so the plus is here, the minus is there for the voltage, so that's 12 volts across it, but the current's going from plus to minus, so that's a plus. That guy is going to be what? That's going to be I0 over 3. I0 is, we said 6 over 3 is 2 amps, that's going to be 2 squared. Oh, sorry, that's not a resistor, so we got to use the source relationship. So for sources, we're going to say the power is I times V, so that's, we said 2 amps times the voltage, which is 12. All that is equal to 0. Let's go ahead and solve the algebra now. Negative 10 times 12 is 120, so that's a negative 120, plus 6 squared is 36 times 2 is 72. These are all watts, by the way. Then we have a 2 squared is 4 times 6 is 24. Then I have a 2 times 12, which is also 24, is equal to 0. Let's hope that is correct. 24, that's going to give me a 48. 48 and 72 is going to give me 120, correct? Let's see. Let's double check. 72 and 48. Let's just write it out. That's a 2, that's 10. That's a 5 and 7. That's 12.